summer school on machine and deep learning for remote sensing application. Today we have a resource person, Dr. Deepu Vijayasenan, and in the first session and the second session, we have Professor Abhik Bhattacharya from IIT Mumbai. So before starting the session, let me introduce the first session speaker, Dr. Deepu Vijayasenan. So Dr. Deepu Vijayasenan is working as a associate professor in the Department of Electronics and Communication at NIT Karnataka, Surathkal. He has obtained his PhD degree from the EPFL and Switzerland, and that ME degree from the ISC Bangalore. And he worked as a research consultant as ASP from 2003 to 2006, and after that he completed his PhD, and later on from 2011 to 12 he was PDF researcher at Saarland University, Germany, and after that he joined NITK Surathkal. His research area includes signal processing, primarily machine learning, deep learning. Also, he works in medical image processing as well. He's executing a couple of projects which are funded by Government of India, SARPA DST and Spark project as well. And he's having couple of publication in the field of the speech and the medical image processing. So I request Dr. Deepu to start your session. Over to you, Deepu.
Thank you, Chandra. Okay, good morning, everybody. So today we will study, or we will rather see an overview of a class of neural network that kind of revolutionized the image recognition, field entirely. Okay. So let's do a recall of what were the neural networks. So we had a fully connected neural network which looks like this. The input, you will give us a vector, you will have some n inputs, and then so what is special is this is a one-dimensional input. So there will be a lot of weights in the first layer that will multiply with it, accumulate it, and find the next vector. Again, this is a vector, that's a hidden output. Again, one more layer, you keep on doing that till you get the output. So there are two things which we need to note here. One is each neuron is computing its output from the previous layer, just the previous layer alone. So the hidden layer only takes the inputs from the input layer. The output layer takes only the input from the hidden layer. So it's stage by stage. The second thing is each of these neurons are connected to everything in the next layer. So each connection has a separate weight. So we have a hidden layer of size 4 in this picture and the input size 3. So we will have something like 12 weights here, banning the bias terms, of course. So we have 12 weights. So even for moderate input sizes, so let's say I have a input which is 200, and let's say I have a hidden layer which is also something like 200, the number of weights in this architecture becomes very large. So if it is 200 and 200, we will have something like 40,000 weights in one layer alone. So this architecture, as the number of input dimensions grow, the number of weight which is required as the parameters, they grow very fast. So that is one thing we need to keep in mind. So what about now if we were to use this kind of networks for vision tasks? So the image is typically having huge input dimensions. So a minimal image where you can see something is typically around 200 cross 200. And they will have something like RG and B channels. So 3 such different images. So this standard image processing competition where you need to identify objects, the input images are something like this. So you have 224 rows, 224 columns, and 3 channels. So this is one of the first big vision task. So the AI systems are supposed to take this input and recognize around 1,000 different classes from here. Now, let us see what is the input dimension. How many numbers do we have at the input? So that is 224 times 224 times 3. Now, that is more than 50,000, okay? I mean, 150,000, sorry, not 50,000, 150,000 numbers are there in the input. Even if you need something like 100 hidden neurons in the first layer, the neural network will have something like 150,000 into 100, that is 15 lakhs of weights or 1.5 million weights. And that's a very small image, right? 200 cross 200 is nothing. It's a very, very small image. Now, what about you have typical small images are like 1 million pixels. So the number of weights goes to billions if we were to look at architectures that look like this. So even with all abundant computing and storage capacities, we will not be able to manage this kind of number of weights or the number of storage that we need. This would be a massive task. So moral of the story is we can forget about training fully connected neural networks that we have seen so far for image recognition, just because they don't scale well. We need a way of reducing the number of weights in the model. So that is where convolutional neural network come into picture. Now, what do these convolutional networks do? That is what we need to look at next. So from an image, we know that there are a couple of properties. It's a spatially arranged group of pixels. Those two numbers which come nearby are very often correlated with each other. So the CNNs make use of that particular property. They don't take this 150,000 numbers of the picture and they don't just make it as a vector. That just says each and every number is not really dependent on anything else. No, we don't need that. So it tries to consider the spatial information in the image also into the network. Now, one of the major property of the image is that they are shift invariant. So what is shift invariance? You take an image, you shift it a little to the right, it is still the same image. You take this cat and shift 10 pixels to the right, it will still look like a cat, right? So this information has to be somehow brought inside the machine learning system. That is what was attempted using convolutional neural network. So the shift invariance also needs, it also implies the following. If you are looking for, let us say, a corner, let's say corner of the ear of the cat at this point on the top, or let's say in the some other feature. So let's say you are looking for a edge like here or a edge here. You can look for similar edges using the similar weights. So we need to actually in image, we need to look for these local features and then somehow put them together. Okay. So, and you need to look for these local features everywhere in the image. So this is the fundamental idea of convolutional neural network. So they typically are trying to look for the same features across different places in the same image. Okay. So we try to have some weights and they try to take those weights which is shared across the images. So that's the key idea. You try not to use independent weights for each and every input number. Rather, you try to look at local features. So every time you look, you don't look from the entire thing. You look from a small region only. And then you try to look for the same feature across across the whole image. So that's what is shown representatively in the illustration here. When you have a set of weights, the weights is only coming from a small set. So let's say it's a 3x3 weights. So you will have, let's say, if you have only one input channel, 3x3 will be 9 different weights. You take that 9 different weights and find the output. And you do that 3x3 across every image, starting from the left top corner till the bottom right corner. Okay, so that operation is what is known as the convolution. We will see that in detail. So there are a few more other kind of layers which comes in convolution layer. There is something known as pooling layer, and traditional fully connected layers are also there, and some non-linearity layers which are typically ReLU layers come in. So we try to see each of these layers in detail now. So first we will see what is this convolution operation. So what is a convolution operation? The convolution operation is a multiply and accumulate operation with some set of weights that we call it as a kernel. A kernel is nothing but a typically small k cross k matrix, something like a 3x3 or 5x5. Maybe can go up to 7x7, 9x9, etc. Not too big. Okay. I think the largest kernels I have seen is something like 11x11, not more than that. So it's a small matrix as compared to the image. Image, of course, we said it can go up to 200, 300, 400 and all, right? So how do we compute the output of a kernel, the convolution? So you take the kernel, first you start from overlapping from the left top onwards. So these three things which are in white here, and you overlap this, you multiply and accumulate all the values. So then you shift the kernel to one column right, then one column right, one column right, until you reach the rightmost. Okay, so here one of the examples is shown. So it's this 9 values 100, 110, 111 getting accumulated with multiplied with this kernel. This is a 101, 010, 101. So you will multiply, you will get this 1, 2, 3, 4 values here. This 3 and this one. This one is getting multiplied with 0. So you get the output 4 here. How do you get this one? You shift this red window to the right. So this 0, 0, 0, 1, 0, 0 and 1, 1, 0. That will get multiplied with this and get this. How do you get this one? The second row, first column one. You overlap it starting with second row, first column. So you overlap here and then keep on shifting. So that's what you do. The kernel is shifted through the entire input size. So the output is also going to look like a image. Okay. So you have an input 2-dimensional image. You multiply with this kernel and accumulate, and you keep on doing that and keep on doing it till you get the output. That is the convolution operation. Please note that the output is a bit smaller than the input. The input is 7x7 and the output is becoming 5x5. So that's because we decided to keep this 3x3 entirely inside this matrix. So the middle point could only start from this point till this point. So sorry. Okay. So if we wanted the original 7x7 image at the output size also, we could have added some zeros, one more layer of zeros to pad the input. So we make the input as slightly bigger by padding zeros. So if the input is made 9x9, we will get the output of 7x7. Okay. And most of the time we put zeros in that extra rows and columns that we pad. This is known as zero padding. Sometimes people just duplicate the value of the nearest pixel instead of padding. That's another way of padding instead of putting zeros. There are different schemes and people have studied different things. But many times people just use this. They just do it without padding also. Okay, so there is one more detail that which we need to see. So this is how typically the convolution operation go. If you have a 3x3 kernel, first it will be overlapped with the left top corner, computed the first output, then it is shifted by 1, put here, shifted by 2, put here, etc. So this is the convolution operation in the typical case. Now, there are a couple of details which I need to tell you here. It is not just multiply accumulate. There is going to be an extra term, bias term also even with. So the kernel, if it is 3x3, it will have 9 weights here plus 1 bias term. So you know what a bias term is. You just typically do a sigma input ij with the kernel ij plus after doing the sum, you will have a plus BM value there. Okay, plus a bias value. So that's one detail. There is a bias value rather than just summing up with the weights. Second detail is you don't always shift this kernel by 1. So here it is getting shifted by 1. So it is here the next position is just 1 pixel to the right. So we assume that that is along the left to right and that is top to bottom. So from left it is shifting to the right by 1 pixel. Once it finishes that row, it will shift down by 1 pixel. So this 1 need not be the case always. So the 1 is actually used quite often, though people also use what is known as strided convolution. So what is a strided convolution? The kernel is going to be shifted by more than 1 pixel. So we don't compute the output for all shift values, but only at fixed intervals. So for example, if we if we fix the stride to be 2, so here we will compute this. We won't compute the second one, we will compute the third one. So we shift by 2. So there will be only one more shift. So this output will be then only 3x3 instead of 5x5 if we do a stride of 2. Okay. So if you make a stride of 2, typically the output size goes almost to the half, right? Yeah, this is a small image, so it doesn't look so much different. But when you have very big images, if you have a strided convolution, you will typically get half of the input. If you make the stride equal to 2, stride equal to 3, it will become almost 1/3. Okay, so this is the full details of one level of convolution. But so far we were discussing about only 2D input, but images are not just 2D. They have within the 2D, they have different channels. For example, RG and B channels. So in general, we consider each of the input as a 3D volume. Okay, so there is height, cross width, cross number of channels. Okay, so it's going to be some n cross m cross number of channels. That is the input. Now also the kernels, now you need to multiply across number of channels also. So the kernels are going to be k cross number of channels there. So same kernel, you just not only accumulate along the height and width of the channel, you accumulate along the total number of channels also. Okay. Now one special detail is that the 3D kernel will be shifted across the length and width of the volume only, and there is no shift across channels. Okay. So when you have one kernel, your output is going to be a 2D image, because you are only shifting across length and height, I mean width and height. There is no shift across channel, because the kernel will already have the same number of channels as the input number of channels. Okay. Now, once you have one kernel, you will get one 3D image. When you have a second kernel, you will have another 3D image. When you have multiple kernels, you will get so many different 2D images. These are actually then stacked together to create a 3D volume. Okay. So this is the full details of a convolutional layer. You have an input, which is a 3D volume. You have a set of kernels. Each of them are 3D matrices, k cross number of channels. Each of the kernel, when you do multiply accumulate, you get one 2D output. And when you do it across all the kernels, you get multiple outputs. And those together, when you do it, you get a 3D volume at the output. So a 3D volume input, 3D volume output, that is what is used in a convolutional layer. Okay. So to summarize, input is 3D and input is a 3D. Okay, I have written not 3D. I don't know why. Input is a 3D matrix and output is a 3D matrix. The kernels are the ones which do the transformation. Okay, now, there are a lot of hyperparameters. We need to fix the kernel size. What is the padding type? What is the number of kernels? What is the stride? That's all hyperparameters. The layer will have parameters which are just the kernel values, and all of them we need to train from the data. So that's the general convolutional layer summary. I'll just show you a demo. So this is one. So far I didn't show you a 3D demo, right? So this is the image in the left side. So it has R, G, and B channels. And there are two kernels. One kernel is 3 cross 3 cross 3, because one has to multiply the R, one has to multiply the G, one has to multiply the B, and there is a bias associated with that particular kernel, right? So how is the first 2D output computed? You take the kernel. So note that we have a 0 padding, so that the output is going to be same as the, oh no, here the padding is different. So, okay, it won't be the same as input, but we have some padding here. Okay. So you just multiply this this 9 numbers with these 9 numbers, this with this 9, this with this 9, multiply, sum up everything, then add the bias. That's how you get to the first number here. The very first number, the output volume, the very first number. So the next one is here. So it shifted by 2. So this is the stride of 2. It shifted by 2. Same filter, multiply, accumulate, you get the second number here. Now again, the third one, you will get the third number here. Now it will vertically shift by 2 again. Earlier it was starting from the first position. Now it vertically shifted down by 2. and it continues. So it keep on getting the first output. Once that first output, so now the first filter is passed through the entire image. Once that is over, now it will compute the second filter. Second filter, it will do the same thing and gets you the second output. Now that output is stacked together to create the output volume. So the input volume was something like after padding, it was 7 cross 7 cross 3. You had filters which are 3 cross 3 size, of course, into 3 channels. So there are 2 filters and the stride was 2. So the output volume was 3 cross 3 cross 2. So this 3 is roughly the half of the 7 because the stride is 2, right? And the number of channels here is going to be the number of filters that you see here. So this is the summary of convolutional layer. I hope everybody is clear about how do we go from one layer to the next layer in a convolutional layer. How do we compute the output of a convolutional layer? Hope that is clear. Okay. Any questions? You can raise your hand and tell me or unmute or. Okay. Let's go to the other layers. So this is the most important layer of a convolutional neural network, the convolutional layer. Now there are a few other layers. The main thing is again what is known as a pooling layer. A pooling layer is something that reduces the spatial resolution of a volume. So we try to use this to aggregate features across space. Okay, that's the purpose of this layer. So remember, we are working with volumes. So it reduces only spatial resolution. It does not reduce the number of channels. Okay. So since this is done, what happens is we said we are trying to look for different features, right? So we try to pass the feature which is max, which is kind of a representation of the neighborhood. So the output is going to be a representation value that represent a local neighborhood. So it kind of reduces the number of parameters in the later layers because your size is reduced, the number of the amount of data which is going into the next layer is reduced. That will reduce the number of parameters in the next layer. So it's a way to reduce the number of parameters, and in some sense that's a way to reduce overfitting actually. So we subsample the input. We only pass one representative from a neighborhood. So here this is known as max pooling. So you have a neighborhood, it will only pass the max value. So this is a pool size of 2. So it will pass only 2 cross 2, only one number. This 2 cross 2, only one number where it passes the max value. Here it is doing a average pooling where it passes, instead of the max value, it passes the average value. Okay. So there are a lot of details about pooling. So there are some hyperparameters. First of all, what is the size of the neighborhood? So F is the size of neighborhood. So you have a neighborhood of F cross F, and we take only one element from here. So for example, here it is 2 cross 2. You take only one from there. Then you have also a stride. How much do you shift? Here, after taking the first representation, you shift it by 2. So you shift by 2. So here it is again, you have a 3 cross 3 neighborhood. Please see that. But you shift by 1. So 3 cross 3 and shift by 1. So the next one comes just after 1. Here in the third example, you have a stride of 2 and it's a 3 cross 3 neighborhood. And typically we use either F equal to 2, S equal to 2, which is this, or F equal to 3, S equal to 2 is also there, but it's not that common. Okay. So there are two hyperparameters for the pooling, the size and the stride. So you take one element from f cross f neighborhood, and after taking that, you shift it by an amount which is equal to the stride. So that is the two different hyperparameters of the pooling layer. Now, in practice, people mostly use max pooling. Okay. Now, some people even try to avoid pooling by doing strided convolution. Because at that time what you do is you compute only the alternate values. Okay, you compute this one, this 2, this 3, and this one only. You don't compute those in between values. That is strided convolution. But pooling is not the same. It actually tries to find the output and try to pass a representative values. So generally, it is observed that pooling is better than strided convolution. So often in practical neural networks, you will see that you have a convolution with a stride 1 only most of the time, but then it will be followed by a max pooling. And you can't use very high values of f and s. Typically, people use what is shown here, f equal to 2 and s equal to 2. You take a 2 cross 2 neighborhood and every time you shift to 2 pixels only. Okay. So that is generally what people keep for pooling. Now, of course, there are too many other kinds of layers which happen in a neural network. I'll just go through briefly. One of the most important thing is what is known as a normalization layer. This is, if you are familiar with any of the neural network toolbox, this is called batch normalization. They were not very popular before, but as the number of layers and as the neural networks get bigger and bigger, they are essential to make them work. So what they do is they try to somehow make the output activation in a standard range. Okay, I am not going into equations for the in the interest of time, but if anybody is interested, we can take it up later. Then the non-linearity layers, they are pretty much the same as whatever you might have seen in normal neural networks. Every multiply accumulated weight is multiply accumulated sum that is actually passed through a non-linearity. And probably the most common non-linearity is the rectified linear unit, ReLU or leaky ReLU. And ReLU is nothing but a half-wave rectifier. I mean, if you have a positive number, you just pass it as such. If you have a negative number, you output a 0. That's what is a ReLU. Okay, and typically in a convolutional neural network, last few layers are going to be fully connected. So as you will see this again with the example, which is coming very soon. As you go from the input towards the output, the spatial resolution becomes smaller and smaller. And at one point, it will become very small, so that we just try to consider that as a set of features without any spatial resolution. We just lay the entire matrix down as a 1D vector and then make a fully, that is known as a flattening. You flatten the 3D matrix and treat it as a vector and continue with traditional conventional fully connected layers. Okay, so that's the typical architecture of CNN. So let us try to see a few examples. Okay, so let us see what a convolutional neural network actually looks like. This is probably the first convolutional neural network that was designed. This is known as LeNet. It's designed by Jan LeCun. This was in 1998. And that's actually even before people were designing deep learning based big neural networks. So this is not so big. So this is called a LeNet 5. It has 5 layers of connections. Okay, so we will see in detail. So this is the reference which I have put here. So 1998. So this was done for doing handwritten digital recognition to recognize the pin code in the letters in USA. This is where the neural network actually has won a competition on that. Okay. So I just want to make the point that there were actually convolutional neural network in 1998, which was before the deep learning era. But however, they became very popular only after the deep learning because people couldn't train a large number of layers in convolutional neural network. Okay, so let us look into the architecture. So the network has actually 2 sets of convolutional and pooling layers. So one convolution here, one pooling here, another convolution here, another pooling here. Then that whole thing is stretched out as a vector, and then there are 3 fully connected layers. That is the 5 layers. So 2 convolution layers and 3 fully connected layers. The input is a grayscale image, and it is actually very small. 32 cross 32 is the input size. So the first layer actually has 6 convolutional filters that are 5 cross 5. So it's since it is 5 cross 5 and there is no padding, so this next layer will be slightly small, -4 basically. That's why this is 28 cross 28. Since there are 6 different filters, there are 6 such 28 cross 28 images. Now there is going to be a pooling, which is actually average pooling. The max pooling came later. So at that time, he was doing an average pooling. So it's a 2 cross 2 average pooling, shift by 2. So this 28 cross 28 become 14 cross 14. Please bear in mind this 6 channels remained intact. That won't reduce. Each of the 6 channel we do average pooling separately. Now, so this was the first layer. So the convolution filters were 5 cross 5. Now the next layer is going to have another 16 convolutional filters. Okay, that's why it becomes 16 convolutional filters. That's how it becomes. So 14 cross 4, and this size was actually 5 cross 5 convolutional filters. So there were 16 of them. So this 14 became slightly smaller, 10 cross 10, because we used again 5 cross 5 convolution. And note that each filter has to accumulate also across the 6 different features. So one convolutional filter here will be of size 5 cross 5 cross 6. And that moving along the whole thing will produce one image. Then the next, second one, third one, like that, 16 different convolutional filters are there. So that's what produced this set of feature maps. Okay. Now, what happens is another layer of pooling, max pooling. So that would give you 16 feature maps, the same, but 5 cross 5 spatial resolution. So the image is now, the 3D volume is now 5 cross 5 cross 16. That's actually 5 cross 5 cross 16 is 25 into 16. That is 400 numbers are here. Now what you do is you take that 400 numbers and make it a vector and use a traditional fully connected layer. So 400 cross 120, that's a fully connected layer. 120 cross 84 is another fully connected layer. 84 cross 10 is the another fully connected layer. And there you have a 10, what is known as the softmax output. So these layers had tanh non-linearity in between, and the final output non-linearity is the softmax, I believe. Yeah. One more detail. I think this neural network is slightly old, so it's not like the typical convolutional neural network where the non-linearity in the convolution layer is ReLU. This had only tanh non-linearity. So, okay. So this is the very first example of a convolutional layer. So couple of things we can notice. The input resolution keeps decreasing. The spatial resolution was 32 cross 32. It became 14 cross 14. Then it became 5 cross 5. So as you go towards the output, the spatial resolution keeps decreasing. That's one thing to be noted. The second thing is, in general, the number of features you keep increasing. First, we had only 6 features, then you had 16 features, etc. So this is a general trend in the convolutional neural network. And then the final, towards the final layer, when the spatial resolution is very small, you try to flatten it and make it as the fully connected layers. So that's the general idea of a convolutional neural network architecture. Okay. Now let us go to the next thing. So why do we do all this convolution? What is special? So the convolutions are used to actually extract simple image features. For example, I have put 2 different kernel values here. So this is one kernel and the bottom one is another different kernel. So if you apply this to a smooth region, for example, you take this image and apply it to this region where all the values are same. So if you apply that, you multiply the same value with the +1 and -1, +2 and -2, +1 and -1. So if there is a uniform input, this kernel will give you 0. But if the intensity is changing between the top part and the bottom part, it will give you some non-zero value. So this kernel, for example, is actually extracting what is known as the horizontal edges. This is the image on the left bottom part is the output of applying the first kernel on the image shown here. So it's actually getting the horizontal edges. The right one is actually the output of the other kernel. And you can see that it is getting you the vertical edges because vertically there is a difference, right? I mean, if there is a difference vertically, this is going to give you a non-zero value. These are absolute values. We don't worry about the negative or positive values. I'm just showing it for the illustration purpose. So if you put together, now if you have another layer where you try to add these 2 elements together, you will get all the images, right? Okay, so once you have these kind of features, you can put them together to make more and more complicated features. For example, if you have this image, you can try to detect the corners. You can try to detect some curve which happens there. So the hope in doing all these convolution operation in the beginning layers of a convolutional neural network is that they will be able to detect elementary features in the first layer, and they will be able to put these elementary features together into more complicated shape in successive layers. For example, maybe first layer it found edges, then it found like corners, maybe then it is trying to put together things like triangles, squares, to create a lot of features for the classification. And once you have all the features in the final convolution layers, then these fully connected layers could take those features and do the classification. This is the hope and this is the rationale behind coming with a convolutional neural network architecture like this. You have a few convolutional layers that hopefully extract a lot of spatial features, and you have a final few fully connected layers that can actually put them together to make a classifier. So that's the idea. Now, is it only saying or is it actually the case? So the happy news is it's indeed the case. We do have ways to figure out what each of those weights learn, and we can figure out what those activations bring in each of the neuron. So this is a output of such a study, which is a neural network for face recognition. So the neural network has a few layers of convolutions, and each of the output which is shown here is basically what is the input pattern that triggers the output of a particular neuron. So this bottom thing is actually the first layer. So you see that around here in the bottommost layer, it is responding to edges at different angles. It is responding to, let's say here, somewhat vertical edge, somewhat horizontal edge, slanted edges, etc. And this one probably is responding to bright spots, etc. Okay, so that's what it learned in the first layer. And the second layer, it is trying to look slightly better. It is trying to look at the putting together two different edges to look at the shape of an eye or shape of mouth somewhere down here, a nose somewhere in between. So these are the things, these are the features that is being activated in the second layer, and towards the final layer it is responding to different face features. So you see that it is successively putting up together different features and coming up with the higher level features. Okay, so that's actually what is the CNN doing. So is that okay? So if that is okay, we will go into couple of more detailed, couple of more CNNs that are very popular. If anybody was working on major recognition, they would have heard about this AlexNet. That's 1000 class classification problem, which we briefly mentioned in the beginning. That 224 cross 224 cross 3 images, and they need to find 1000 different objects in those images. And this is the neural network that actually won the challenge in 2012. And this is the first CNN that became very famous, rather than Jan LeCun, which was the first one. This became famous because it has won the ImageNet object classification challenge. And not only because of that, it actually reported more than 20% error reduction as compared to the second place winner. So this outperformed a lot more than the other methods which was proposed at that time in 2012. And other methods were actually based on support vector machines, where you have to figure out what feature to give the input, etc. And AlexNet didn't bother to about features. That's one special thing about convolutional neural network, right? As we said, the first few layers extract the features, and then the final layers do the classification. It's doing both features and classification together. Okay. So that was actually the revolution. So the convolutional neural network, together with learning the features as well as classifications, are able to outperform any other competing methods such as SVMs. This was back in 2012. And that's when it had become a revolution in CNNs. Okay. So let us take a close look at it. The first layer has a strided convolution. Okay. It's not one shift. So this has 11 cross 11 kernels and 96 of them. So the input is 227 cross 227 cross 3. So 11 cross 11, but the stride is 4. So this is roughly 1/4 of it. You will see that 55 into 4 is something like 220. And there are 96 such kernels. So there are the output volume is 55 cross 55 cross 96. There is a max pooling 3 cross 3 and shift by 2. So roughly it becomes half. There is no padding in this convolution layer. So we get before going into the next layer, let us think how many parameters we do have in this first layer. You know that it is 11 cross 11 convolutions. So also you know that it's 11 cross 11 cross 3 channels. So each kernel will be 11 cross 11 cross 3. That's actually 363 numbers. There will be one bias term. So therefore 364 parameters will be there in one convolution kernel. There are 96 such convolution kernels. So the total number of parameters of this convolutional layer is going to be 364 into 96. It's around 35,000. Okay, so I'm just giving you an idea about what's the number of parameters. Of course, there is a ReLU non-linearity followed by that, and then it is going for a max pooling. Okay, there are no parameters there. Then you have a 5 cross 5 convolutions, and you try to pad so that the output is also 27 cross 27. There is a max pooling operation, so that becomes roughly half, again 13 cross 13. You have 3 cross 3 convolutions, again 3 cross 3 convolutions, one more 3 cross 3 convolution, then you have a max pool. So this becomes 6 cross 6 cross 256. Okay, so you see that the number of features is increasing and the resolution is decreasing. Originally the resolution was 227, became 55, became 27, then it became 13. It stayed in 13 for some more convolution layers. Then it became 6. So you have reduced the spatial dimension a lot. And in the meantime, you have increased the number of features. Here you only had number of channels 3. You had 96 features. This stayed 96. Then it was increased to 256. Increased, this is max pool, so it won't affect. In the convolution, it stayed at 384. And okay, here it didn't increase. It stayed at 256 only. But it has gone from just 3 channels to 256 channels. So the spatial resolution kept decreasing and the number of features kept increasing. So that that entire thing is then flattened out as a 9216 vector. This is same as the 6 cross 6 cross 256. And then there are a couple of more fully connected layers, and that has come to the output. So the output is 1000 different outputs of MAC layers, because we have to tell 1000 different things apart. Okay. So this has around 60 million parameters. Okay, that's not small, but it also had a lot of data to train with. We will come to that a bit later. Okay, so let's go to the next one. The next one is VGG60. So this was in 2012. Another major one, this was in 2015. This was, as the name indicates, it was a 16-layer neural network. And there were a couple of specialties regarding to the previous one. Previous one, you have to remember each and every layer. I mean, each and every layer was very ad hoc manner fixed. Some was 11, some was 5 cross 5, some was 3 cross 3. Sometimes you had 384 features, sometimes you had 256 features, and so on. Here, people tried to make it slightly normal. So you have 2 layers of convolution always, and then followed by a pooling. And after every pooling, you double the number of features. So first you have 64 features, and all the convolutions are 3 cross 3. That is the special about this neural network. Every time it is 3 cross 3. Every time you go from, you do a pooling. So this was 224. Then you pooled and made 112. Now you will have 128 filters. Now again you poll to make it 56. That 128, then you make it double to 56. Then the 56 goes half. Then that 256 you double in the next step. Again, this 28 you poll to make a 14. You double the 512 to, oh no, you don't double after the 512. Okay, 512 you make another one more layer convolution, and then you try to make a small resolution and then do a fully connected layer to get the softmax. Okay, so so every time you kind of halve the image. From 224 it went to 112, went to 56, went to 28, 14 until 7. Meantime the features doubled: 64, 128, 256 and 512. Okay, so again this was the neural network actually won the ImageNet competition in 2015. So it's still old. Okay, so the architecture for object classification task is to start with a few kernels, keep increasing the number of filters, and at the same time keep on doing max pooling to reduce the space resolution. At the final few layers, you keep on doing fully connected layers to get the classification. That's the general architecture for a object detection class in convolutional neural network. So there is okay, I have half an hour. I think I have time to complete the thing. So there is one more very famous neural network that came around 2015-16. This is known as ResNet, and this is so far people have trained things like 16 layers, 18 layers, etc. Okay, now this particular technique had enabled people to train much large, deeper neural networks. So the elementary building block of what is known as the ResNets is a residual block, which is shown in the picture. Okay, so let us examine what it is. On the left side of the picture here, the left side picture, this shows a two-layer from a conventional convolutional neural network. So normal convolutional neural network, you have some input layer, a weight layer perform multiplication activation, another weight layer followed by another activation. So this is what happens normally. Let us call this as the main path. So input, weight, multiplication, non-linearity, multiplication, non-linearity. In a residual block, there will be a shorter path bypassing the main path. The input is added to the output coming from the second weighted layer before passing to the non-linearity at the second output. Please note that this requires the dimension of this f of x and the input x to be the same. Otherwise, you won't be able to add it here. That restricts the number of hidden outputs, padding size, etc. But that's okay, that's a detail. So this path provides a way to skip two sets of multiplication. So if something goes wrong in these two layers, it will still be able to have these features going towards the output. So this is a way to skip, this bypass is a way to skip this two weight multiplication, and that is popularly known as a skip connection. Okay, there is one more detail that you need to keep in mind. This network and this network has the exact same number of parameters. There is no extra parameters introduced in the skip connection. It is just taking this value and adding it there. There is nothing special there. There is no weight there. Only the parameters of the neural networks are in the main path, not in the bypass path. So this before the ResNet period, something people have noticed. Even if you make a network deeper, the training error does not get better. So it should learn better because it has more parameters, but it was not happening in practice. So the picture is from the actual ResNet paper. The left side shows the results from the network that do not have skip connections, which is called as a plain networks by the paper. The dotted lines here denote the, okay, so the left side shows the results from plain networks as we told. So even after training, so this yellow line is a 20 layer network. This 56 layer network actually has a higher error, both in training and testing. The below part is training, but even in training, the error of the larger network is higher. That should not have happened. And here, the right side, it is the exact same network with adding skip connections. So you see that the error actually reduced a lot. Not only that, now the 56 layer network actually has a lower error than the 20. The 20 layer here in the right side is actually better than the 20 layer on the left side, even with the skip, while adding skip connections. That is same number of parameters, but only with some more connections. The skip connections, the ResNet is getting better than a same number of parameter plain network. Not only that, with the ResNet, higher number of layers are getting better than the smaller layers. So that was a revolution around this 2015-16. It was a major breakthrough. So you can see that the situation completely reversed. Now the bigger networks are better. They are also decreasing the validation error much higher. So this is coming here around 5 to 6%. Whereas here it was 20% even with the minimum value validation error. So this was a breakthrough again. So this was actually some of the architectures. The top picture shows the architecture of a 34 layer ResNet. Note that there are convolutional layers. The output of a convolutional layer is added to the skip connection 2 layers later, and that's what it keeps on repeating. So, and finally there is a softmax layer, fully connected layer and all. Okay, so that's the, so there are different people have explored multiple ways to do skip connections. Here are a few of them. This was a 2 layer and addition. There is okay, people have introduced batch now. Without that, these things doesn't work. So there are 2 layers. You add and then do a batch normalization before non-linearity. There is no ReLU in the in the output side in this example. Okay. So this was actually, as I mentioned, this was a quantum jump. So this was 2010, where the errors were in the, so this was about ImageNet classification. When you find the best 5 classes, do you get into error or not? Around 2010, the error was 28.2, then it became 25.8. It reduced slightly by 3%. But in 2012, with AlexNet, it suddenly dropped from 25 to 16, something like 9%, 9.4%. That was a huge reduction, you see. Then there was, I don't remember what was this. 2014, it was VGGNet. 2013, it was still somewhat modified version of AlexNet, I believe. 2014, it's a VGGNet. That was with the 19 layers. So then there was a GoogleNet, which was 6.7%. And then 2015, the 6 became 3.5. It's almost halved again. And the number of layers, so it was a ResNet 152 layers. Okay. that has made the error half. So you see from 2012 to 2015, the number of layers went up from 8 to 150 and the error went from 16 to 3%. So that has become pretty, that was a very, very huge achievement in the side of image detection. So, okay, I will skip this slide. And one small thing about the convolutional neural network is the training of the convolutional neural network. That's the last part that I want to cover. I think we will finish it. So what is going to be the training algorithm of convolutional neural network? Surprisingly, the same backpropagation algorithm which you use to train the normal feed-forward networks, it will work. Only point is, now the layers are not fully connected. You need to backpropagate only through a selected set of nodes. However, there is some detail, a couple of details that I would like to share. One is that we need typically differentiable functions to do gradient descent. There is one place in convolutional neural network where we cannot differentiate. That is the max pooling. So you have to track the gradient, and there is something which you need to do special for that. You need to track from where the max value came and backpropagate only to that node. Now, that's okay. That's a small detail. But the bigger detail is that the number of parameters is huge. I mean, you see that VGGNet has something like 130 million parameters, right? Even after embracing convolutional neural networks, this 130 million parameters is not small. So you need lot of data to train them. Okay. And in speech, there was a saying, there is no data like more data. Whatever data you keep on getting, you use it. Now, with the deep learning, everybody has to say this, whether it is speech, image, or whatever it is. So there's nothing like more data. You can use all the data because you have very complicated model. And in this case, you need enormous amount of labeled data, which is sometimes not possible. So you try to do a few more tricks called data augmentation, transfer learning, etc. So how much data do you need to train 130 million parameters? More than 130 million, definitely, right? Do we have so much labeled data? Most of the time we don't. So how do we overcome this? Hello, is there a question? Okay. So one of the answers in solving this data problem is to synthesize the data. So for example, you take a cat and crop a little bit this side, it should look still like a cat. You can also do other geometric transformations such as mirroring, random cropping, rotations, little bit of shearing. So we are actually using our visual knowledge here. That is, even if the object is slightly rotated or left side, right side flipped, it is going to be the same object. That takes care of camera effects such as zooming, tilting, etc. Okay. Now, so there are also other options to shift the colors a little bit. So you can recognize the object even if you shift the color a little bit, right? They don't change the object. So it could even mimic the color variation when you view it in different light settings. So for example, okay. So moral of the story is, how much ever data you have, you will need to do data augmentation while training the convolutional neural network. These methods are pretty elementary, but they are very powerful. There are also other kind of advanced methods, which probably we will take it up some other time. The other thing is, often you don't have any data. For example, let's say you are faced with a new application. Let's say somebody gives you and tell you, you need to do leaf recognition. Now, if I were to do the same thing what ImageNet people did, we need to go and climb trees and collect 1 million images of leaves. That's not possible, okay? There is actually a data set for leaf recognition. If you look it up, it is called a leaf snap. If you look it up, there are close to 200 classes and around 5 or 10 images each. You can't collect 1 million samples of these leaves, okay? Now, obviously we cannot collect 1 million images. Now, how do we do this? Fortunately, it turns out that we could benefit from a neural network trained on any other large object detection problem. So remember, we showed you what is the neural network's learning. The first layers, it is actually learning pretty general features like horizontal edges, vertical edges. Even the next layers, it was learning kind of corners, curves, etc. So remember, we had all those huge networks trained on millions of images. And they could detect 1,000 different classes, that including cars, buildings, trees, chairs, tables, etc. So if those networks had learned elementary features that could differentiate all these 1,000 different kinds of classes, we hope that they might have learned something fairly general. And we could generalize those at least initial level of features to any object classification challenge. Okay. So what is the moral of the story is, we try to start from an existing neural network, and we only, for the new task, we only train a couple of layers, maybe 2, maybe 3. That's it. You don't train everything. So for training 1 or 2 layers, maybe the data which you have is enough. So all those features which it has learned on the large data set is still useful. Okay. So that is the idea behind transfer learning, which is a very crucial thing. Whenever you can do transfer learning, please do it. Okay, with that, I think I would like to conclude the talk. I think we just saw in short what is CNN. They are very special architectures for images doing computer vision. They incorporate the shift invariance in the convolutional layers. Some of the very deep architectures are convolutional network. We saw ResNet, which is having 150 layers. And typically for object recognition, there is a set of convolutional layers followed by a few fully connected layers. And data augmentation and transfer learning are essential as part of training these things. You definitely need data augmentation and you definitely need a transfer learning if that is possible. Of course, there are a lot more other types of fancy convolutional networks for many other tasks. I think we will probably will not have time to do all those today. Thank you. Thanks a lot. I think the floor is open for questions.
Thank you, Deepu, for delivering a fundamental concept of this senior architecture.